All right. Thank you for the introduction, and thank you, everybody. So it's my opportunity to open this technical plenary, and I would like to do that by starting with a question for you all. So what do you think consumes most energy overall? Data centers or telco network? So think about that for a little bit. Take a bit of time. And once you make up your mind, I want you to point one direction, right? This way for data centers and that way for telco. Just be mindful of your neighbors, right? So maybe like more like this way. Come on, don't be shy, don't be shy. Okay, so now I have the impression that everybody's cheating and is showing both ways. So it works much less than I thought it would work. Okay, so let's get the suspense. Last year, estimates are slightly above for telco than data centers. Right? The ballpark is kind of the same with a slight heads up for telco. What I found more interesting is how this evolved over time. So if we look in the 7 years prior to this, telco were already a bit ahead, and we see a somewhat comparable improvement or increase in energy usage by both. What is more interesting, in my opinion, is the increase on useful work done by those systems. If you look at data centers, 300+%, telco networks, 600% increase in traffic. What does that really tell us? It tells us that both of those systems have significantly improved their energy efficiency in that time period. However, it also tells us that this increase was not enough because the change in energy is still positive. Now, here's the issue about this. It is fairly easy to keep deploying additional network capacity and to build more data centers. It is a lot harder to keep increasing the energy efficiency with which those systems operate. So here's what is unfortunately likely to happen, that we're going to keep doing those things, and the total energy usage will keep increasing. And that is a problem because as of today, producing energy emits carbon. Even though there have been great uptakes in renewable energy production, as of today, more than half of the worldwide energy production still comes from carbon-intensive sources. So this is why today I would like to pitch two ideas how we should make tomorrow's internet more sustainable in order to reduce its carbon footprint. I will touch about two of the many ideas we've been discussing in my group since a while now. That will pertain about the operational footprint, so the energy usage while the network runs, and its embodied footprint, the carbon, well, I'll introduce that later. So let's start with the operational footprint. 2 decades ago, academics made this somewhat provocative claim that the internet core consumes more energy per byte than wireless LAN. And actually, they made some rough calculation that shows that it can be consuming actually quite a lot more. So how can that be? How can that be true? Well, it's a combination of at least 3 facts. The first one is that network devices are typically always on, okay? The second is that network devices have an energy profile that is essentially independent of the load. That means you pay most of the power costs, or the power cost to put the device on. And then as you keep loading it with more and more traffic, the power does increase, but not that much. Fine. The issue with this profile is that network tends to be underutilized, right? And that is kind of more of a feature than a bug, right? But ISP typically over-provision the network because they want to provision for peak traffic, they want to provide resiliency. So that starts from a good mindset. The problem is that in conjunction with fact number 2, it means we are spending most of our time operating in the least energy efficient region for most devices in our network. Here are some example data from our partner at Switch in Switzerland. If you look at this weather map, colors, and you see the color scale here, it's essentially all blue and green. That means utilization below 20%. Other data sets show the same patterns. Here's a cloud provider in France, similar thing, 18% average over the 2 years of data we've looked at. So essentially, you get the red curve for a typical network device, and what you want for energy efficiency is the proportional line, right? So how can we go from the red to more proportionality? You can do that in essentially 2 ways. The first is to try to run your network more often at high utilization regimes. And the second is to try to reduce the low utilization power usage. Ideally, you would do both. The basic idea to do this is not rocket science, is turning things off when you don't need them, right? So in a router or in a switch, what could you turn off? Well, the easy things to think about are ports, eventually line cards, if you're lucky, maybe entire devices, but that seems a lot less likely to be possible. But also things that are less obvious. Like if you partition your memory, maybe you don't need all of them, and you can turn some memory banks off, or redundant power supplies, or LEDs, as was discussed at the last RAG meeting. Things can be also less, abrupt than on or off, right? You could also consider reducing the rate at which you configure your ports. You could downclock your ASIC. You could maybe cache some very useful feed entries and turn off the rest of the memory for some time. As I said, this is nothing new. Academics have toyed with those ideas since 15 plus years, and it was discussed by some of your colleagues 6 months ago at the last RAG meeting. So what does the theory tell us? The theory tells us that we could save tens of energy percents in low utilization networks. I'll let that sink for a second. Like 2 digits, multiple of them, if your average utilization is below 30%, which we've seen to be fairly common in ISPs. How could you do this? Well, essentially, the idea that was suggested by academics was to say, if we tolerate a one-time increase in delay of, say, 10 milliseconds for your traffic, then you could buffer traffic for 10 milliseconds while you put your thing off. Then you wake up in, say, 1 millisecond, and then you send your burst of traffic. And if you do things right, you will pay the price for the burst only once in your network. So delay will be kind of bonded for significant energy gains. Now, the trick here is that this is theory. And theory does not align with practice. Right? So the key caveat is that as of today, if you take a transceiver off, it will take seconds to turn it back on. Right? So those are measurements that we've performed in the lab, taking the transceiver we had and the routers we have. So I don't claim generality about the numbers there, but the orders of magnitude are more likely to stay the same whichever transceiver and device you take. So essentially, the transceivers today are 1,000 times slower than what we would need in order to do this buffer and burst strategy and save energy by doing that. So why am I mentioning this? Because I think we can still do this sort of things if we change the time scale. Right? I showed this graph before, and it should not be a surprising looking graph for many of you. We have strongly daily patterns in most ISP networks. It means that we have some change and predictable change in capacity in traffic demand between daytime and nighttime. And on those time scale, it's fine to take 10, 15 seconds to turn something on and off. So we've been toying with this idea and thinking protocol this. And if you play that game, you quickly realize you have essentially 3 questions that kind of you need answering to. How would you play with the control plane, the rest of the control plane, so that you don't trigger reconvergence all the time? Which signal will you use in order to put things to sleep, and more importantly, to wake them back up? And what is the performance cost? So quick answers to those 3 questions. How do you play nice with routing? It's actually not that big of a deal, because we're anyway saying that we cannot do this very fast. So it's going to be a couple of times a day, maybe 1 or twice per hour anyway. The convergence of OSPF is going to be way faster than this, even if you do it in naive way. So that's not really a problem anymore for this sleeping use case. Which signal can you use? Well, there's many to choose from. We started with the simplest thing possible, monitoring the link utilization, which is something that is already measured in many networks, and you can collect easily using standardized OSPF extensions, already standardized OSPF extensions. Now, the more interesting is the third one. How much does that affect the traffic? Well, essentially, not that much. I'll try to explain you the intuition why. So this graph here shows a number of TCP flows and when they start and when they end. So we compare the same network and the same traffic demand on cases where we do and we do not put links to sleep. So the green bars show the time the flows start and end, where we have no impact when we do put things to sleep. And the bars turned red in the cases where some flow completion time is increased by the fact that we turn some links to sleep. So there are two things to observe here. The first one is that we actually don't see a lot of red. There is some, it's there, but it's not that much. And it is located in time or we observe some red parts where the flows would normally finish while the network is waking up. That means on those tiny portion of the time during the day where we would be waking up the network, it is possible to see some flow completion time increase. More importantly, and what you don't see on the graph, is that all that happened essentially without any extra packet loss compared to the standard case where you don't put anything to sleep. Why is that? Simply because congestion control is doing its thing. Like if we start building congestion, the congestion control protocols will, scale back and take their fair share and keep the network running. It's not like we're not in a link failure scenario. We are in a slowly increasing congestion scenario. And actually, we had to work quite hard to even see those effects, because you need to be, in order to see increase in flow completion time, you need to have the just slight congestion event that are bad enough to see the increase, but not so bad so that you would not have congestion if all your links were awake. So it's actually quite subtle to make those things even happen. In summary, playing this game, turning links to sleep at longer time scale is essentially a traffic engineering problem. Slightly different objectives. It's not just about flows goes where, but also which links do we really need to serve those flows. And we've been solving those for a while. We know how to do this at, say, 5 minutes interval granularity. So here comes the question you might asking yourself, okay, so if we do this, how much can we really save? I'm sorry to tell you that I cannot answer this question as of today, because there are two key things we miss. We lack measurement data and we lack test cases. So one key problem we are facing is that when you buy a switch or a router, the datasheet will only tell you about the max power. But as we discussed, the device is almost never used under full load, right? So they don't consume the max power, and often enough, very far from this. So what is the typical power usage of a router? Well, we don't really know, but we're trying to figure it out, right? So we are doing the simplest thing you could imagine. You take a power meter, you put it in serial between the power plug and the power supply unit, and you apply different control loads, and you see what happens. And we're starting building such models, and they are pretty intuitive, right? There are combinations of terms you would expect. What we call static power, which is independent of the load, but dependent on the device configuration. Then the traffic dependent part, energy per bit, energy per packet, and then things that are indirect consequence of the traffic, fan power and power conversion losses. The point here is that we do have this approach of how we would model this so that we can estimate the effective energy usage, but we need a common understanding of how we would instantiate those models. And it's part of the ongoing work we are trying to do with some IETF folks. So we have an approach, but we don't have the devices that should be measured, right? So what we've been working on is essentially a prototype box that we can send to you, and then so like, here's the Mac that needs access to the public internet. Please plug this device in, and then we'll start collecting data that everybody can access. Eventually, the vision we have is some sort of an extension of RIPE Atlas or RIPE Stat with power data that we currently don't have, as far as I know. Second is that we lack test cases. I mean, realistic ones. I showed this slide before that was kind of maybe intricate and complex. It's intricate and complex because in simulation, we can create anything we want, making things arbitrarily good or bad. But what would happen in practice? For that, we need to know real network topology and real traffic demands, which we don't have. So in summary, I think there are ways to improve the operational footprint of networks by putting things to sleep, but we need your help in order to really quantify whether it's worth it to do it or not. Now, shifting gear a little bit, I want to briefly mention something about embodied footprint of networks. For those of you that are not familiar, the embodied carbon refers to the footprint of products in the rest of the life cycle, excluding their use phase. In consumer devices, this tends to dominate the overall carbon footprint of a device. As you can see here in dark, the embodied footprint versus the use phase. For network devices, it typically tends to be the other way around, right? The use phase operation carbon emission dominates. But this is not because they're better built or because they're better recycled. It is because they are on all the time and they operate all the time in their least efficient operation point. So it's actually, even though the bar looks small because there are far fewer user devices than, there are far more user devices than network devices, we have a real problem there as well in the embodied footprint. How improve this? It's pretty simple. Just keep using your device longer. When I made those slides, the first version of the slide a couple of years back, it was still the standard at 3 to 5 years refresh rate, at least for big networks. I'm glad to see that since then it has starting to improve and people are starting to extend this. Maybe not always for sustainability reasons, but still. But you may wonder, if we were to do this, wouldn't we make the networks like less reliable, less secure, or harder to manage? Not necessarily, I would argue. So it is said that the vast majority of network hardware failure takes place in the first 30 days of installing new hardware. How could this be? Well, it's actually a fairly well understood thing from people studying reliability engineering. And the reason is, as shown on the graph here on the right side. The failure rate of a manufacturing product is a combination of 3 factors. On the red, you see what is known as the burn-in failures. That is essentially all failures that happen when you exercise for the first time a defect in manufacturing. Then you have a plateau of random failures. And eventually you have the wear out effects. So the failures that come from aging of the hardware. But we argue that, or we hypothesize that it's very unlikely that device that run without fault for 3 years is going to start failing soon after. And we see two empirical evidence of this. The first is that most vendors provide a 5-year window of support for any device they sell after they stop selling it. So from day one, they have like at least 7 to 10 years of support. And provide unlimited warranties for refurbished hardware they bought secondhand, they are reselling, and they're still confident that it's not going to start failing. So we need to really understand better how network devices age. Essentially, what we need to do is to get data so that we can plot those things and see where or when the aging effect starts to appear. And to do this, we need data that we don't have. We need data from the operators of network. When do they renew hardware? So when do you renew hardware? Why do you do it? Of course, it's not just about aging. Sometimes you need extra capacity, and this is what drives buying new hardware. That's fair, but when does that effectively happen? What type of failures did you see in practice? When do those failures happen? Which failures are they? I don't have time to get into the last 2 points. So I want to wrap up this part. I think it is also possible to reduce the embedded footprint of networks. We have ideas of how to do this. It's simple. You should renew only when we really need it, but it's quite hard to estimate when that is. And we can help you trying to assess when it is really necessary. In summary, we need your help in order to help your network. Right? We need data. We need test cases for those energy saving ideas. We need access to measurement of devices in the network that you operate. And we need better information about how networks are being managed, how hardware is being maintained and bought and replaced. Academics have ideas. Operators have the power. They have the power to pay for at the end of the month, and they have the power to change things in the network. So I really, really think that we should be working together in order to make tomorrow's internet more sustainable.